Welcome to this third part of the open courseware dedicated to the hydrometallurgy treatment of nickel and cobalt ores. This part will be focused on the development of the atmospheric leaching process, the process developed by ERAMET. I remind you this diagram and with the main advantages of the ERAMET process, and I will tell you all the story, all the development, and why we have concluded to such conclusion. To remind you, you have here the laterite ore body with the weathering profile. On the upper part, the limonite, very rich in goethite, level of iron oxide up to 75%, and on the lower part, the saprolite with magnesium silicate, lower iron concentration but very high magnesium concentration. The process, I tell you that already, will be done in the same vessel with leaching of limonite, saprolite, and reprecipitation of the jarosite. How does it work? During this leaching, you have the dissolution of the oxide, magnesium silicate, of the iron oxide, of the nickel oxide, of the cobalt oxide, consuming some acidity in order to put in solution all these elements. This part of the process, the main parameters is the kinetic of the dissolution. After that, you have all the species in solution, and in the same time you reprecipitate the iron as jarosite. And the process is managed by the kinetic of precipitation. This picture is the jarosite crystals. It's like cubes. You see the dimension of the scale, it's 1 micron. The jarosite is cubes at the level of 10 to 20 micron. The main chemical property and parameters of all these different parts, that's dissolution kinetics, the equilibrium of the species in solution, and the precipitation kinetics of the jarosite. And the main thing is that the acid needed for dissolution is regenerated during the precipitation. How does it work? We have here a simplified flow sheet of the process with the mixture of limonite and saprolite, put it in seawater, leaching with sulfuric acid, primary neutralization with limestone to neutralize the acidity, countercurrent decantation to separate the residue from a leach solution. On the leach solution, we have a secondary neutralization, a solvent extraction to separate cobalt and manganese, cobalt recovery, manganese recovery, and on the mainstream, nickel precipitation to recover the nickel product. And at the end, the liquid treatment. I will detail you all these different parts of the processes. That's a simplified flow sheet. That's a more complicated flow sheet. With here the ore preparation, primary neutralization, atmospheric leaching, primary neutralization, and so on. And you see that in this flow sheet there are different loops of solution or of solids. Here another loop, there is another loop here. These loops are very important to increase the quality of the product and to have a very good yield of recovery of nickel and cobalt. First part of the process, that's ore preparation. You see, on the mine, you will have different type of ore, the rocky saprolite, the earthy saprolite, and the limonite. You will mix this different type of ore, and you will crush it in different equipment, a SAG mill and a ball mill, in order to obtain a very fine ore. The grain size of the ore is 100 micron. I present you that, but in the reality, grinding is done under seawater, and what you obtain after grinding is a pulp. We call that a pulp, a mud of a mixture of seawater and ore. And that's the input of the hydro process. The first part of the hydro process will be dissolution of the ore. You add sulfuric acid. By adding sulfuric acid, you dissolve the nickel, the cobalt, the iron. You put all that in solution, and you reprecipitate the iron as jarosite. This operation is done in a series of mixing tanks in order to have a certain time to do the reaction, and at 100 degrees C. You obtain that, a solution, dark green. Green is nickel, dark is due to the presence of manganese and cobalt in the solution. And we call that the pregnant leach solution. And you reprecipitate the iron in the leaching residue. In this leaching residue, you have the jarosite, the iron, but you have also other insoluble species as silicate, as chromite, and also as there was some neutralization with limestone, there is also gypsum in this precipitate. After this dissolution part, you neutralize the solution by adding limestone, calcium carbonate, in order to neutralize the acidity, the remaining acidity, and you form gypsum, is a solid, mixed with jarosite, and you separate it by contact current decantation. You see here the solution and the decantation of the residue of the small part, small flux of the residue, and the thickening of this residue on the lower part of the decanter. After this decantation, you filtrate, you wash this residue, you filtrate it on a press filter, and you obtain a very beautiful cake. I have a sample of this cake. It's a solid residue, and you can store it after. This residue has no value, but you have to manage the residue and to see if it is chemical inert, and we have done a lot of tests to prove that this residue is completely inert. That's the reason why we have a very specific area to manage this residue, to neutralize it, and to eliminate the water in order to obtain a rather dry residue. This iron residue is compliant with all the different stability criteria depending of the environmental standards, and it's in relation with the kind of storage we will use for this residue. It's very important, this residue. I remind you that the ore is an iron ore, and there is only for 1 ton of ore there is only 17 kilograms of nickel in the ore. All the remaining part, that's iron, and such process, it's a plant to produce residue. And in this residue, you add some sulfate due to the fact that you have precipitated jarosite, and you add also gypsum, calcium sulfate. And for 1 ton of ore, you will create 1.5 ton of residue. It's a plant to produce residue. And it's very important during the development of the process to know what to do with this residue and how to stockpile this residue. Very, very important. The next part of the process is the solution treatment, the pregnant leach solution. You obtain this solution, and on this PLS, pregnant leach solution, you have a secondary neutralization with limestone in order to precipitate iron, aluminium, and chromium. If necessary, you have an oxidation of iron 2 in iron 3 in order to be able to precipitate the iron. you obtain a solid containing chromium, iron and aluminium, but at the pH you have used to neutralize, there is some precipitation of nickel, and as you want to recover the maximum of nickel, you have a secondary treatment of this residue in order to recover the remaining part of nickel in a solution, and this solution is recycled on this step, and you obtain a final solid with this iron, aluminium, chromium, and you send it to the CCD, and it will be mixed with the residue. The second part of this step is the solvent extraction. I will explain you more in details after that. The principle is to use an organic liquid called CyanX 272, and this organic liquid can recover selectively cobalt and manganese from the nickel solution. How does it work? That's just a slide to present the reaction of secondary neutralization, and in order to precipitate the aluminum sulfate, the chromium sulfate and the iron sulfate as hydroxide here, and then the solvent extraction. How does it work, solvent extraction? You have specific organic phases with a specific material in it that could recover selectively nickel and cobalt. You take this organic phase, you mix it with the aqueous phase, the prenanclear solution, you mix it like that, and during the mixing there is a translation of cobalt and manganese from the aqueous phase to the organic phase, and the result of such mixing is you see that after decantation you have a decantation stages with a heavy aqueous solution and light organic solution, separation by decantation of the two solutions, and you recover a solution with only a nickel and an organic solution with cobalt and manganese. The blue color is due to the cobalt in the organic solution. That's the first step. After that you have a second step. You take this organic solution and you wash it to recover some remaining part of nickel. And the last step is the stripping step, the regeneration of the organic phases. You put another acidic solution in order to put all the cobalt and manganese in aqueous phase, and the pink color is due to the presence of cobalt in this aqueous phase. You see this last step. And solvent, the organic phase, is regenerated and is reused to the first step, to the extraction step. It's a way, it's magic. With one solution containing nickel, cobalt and manganese, you obtain two different solutions, one with only the nickel and the other one with the cobalt and manganese. And the solvent used for that is continuously regenerated and reused in specific device called mixer settler. On this picture you see mixer settler at pilot scale with different parts. Here you have the mixing part with a turbine that mix aqueous and the organic phase, and then the decantation part to separate the two phases. And you do that in a series of mixer settler with extraction here and elution recovery of cobalt here. And after that, a regeneration of the solvent and reuse of the solvent at the beginning of the mixer settler. This operation more in details. The organic phase, you see it's a phosphine dilute in classical organic carbon phases, shell salt D70, and in the aqueous phase, you have the nickel, the cobalt, the magnesium, the manganese, and the zinc. There are some zinc also in the phase, and you use the cyanide here to selectively recover the manganese and the cobalt, and forming these spaces in aqueous phases. On this diagram, you see regarding the pH and the yield of extraction, you see here the nickel extraction curve at rather high pH, the manganese and cobalt extraction curve at pH about 4, and zinc extraction curves. This diagram indicates that to recover selectively manganese and cobalt, you have to be at pH 4 during the extraction and not at pH 6, because at pH 6 you will recover also the nickel, and you don't want to do it. More precisely, to know the dimension of the mixer settler, you use such diagram. It's what we call an isotherm of cobalt extraction with this curve, and you draw this line to have the different steps of cobalt extraction. And in the reality, the cobalt and the manganese solvent extraction will be divided in different steps. You have the main step here, the extraction, with the aqueous phase that enters the mixer settler devices, and in a countercurrent way with the organic phase. Extraction here of cobalt and manganese, and cobalt and manganese are in the organic phase in this step. Scrubbing, I show you that, to recover the remaining part of nickel content in the solvent, and after that the stripping, the recovery of the cobalt and manganese in 3 mixer settler, and you have a specific recovery of zinc due to the fact that zinc is very well extracted in the solvent, and you have to use very high acidity to remove the zinc from the solvent. After this last stage of stripping, the solvent is regenerated and is resent in the beginning of the process. I said you that you have to manage the pH to be sure that all this part is at pH between 4 and 5, and to manage this pH you add some sodium hydroxide in order to continuously lower the pH. The first part is done by pre-neutralization of the solvent, and then the second part is done directly in the mixer settler. Next step is very important, is the recovery of nickel on the solution obtained after the solvent extraction. To recover the nickel is rather simple. You add soda ash, sodium carbonate, to precipitate nickel carbonate. That nickel carbonate, you precipitate it and you recover it by filtration, and that's the product of this process. You see here a picture of nickel carbonate produced during the pilot campaigns, and you have here the equation, the reaction of nickel carbonate addition on nickel sulfate in liquid and precipitation of this nickel carbonate. For the other part, for the cobalt and manganese solution, we precipitate selectively cobalt sulfide by adding sodium sulfide, and you obtain this brown, rather gray product, that's the cobalt sulfide. And it's rather selective, and you obtain a product with more than 50% of cobalt content. And after that, on the same solution, manganese is remaining, and you precipitate manganese with adding calcium hydroxide, lime, to precipitate manganese hydroxide. That's the different steps: cobalt recovery, manganese recovery, and cobalt will be a semi-product. Cobalt has a certain value, and in these steps, manganese at the present time has no value. To have a comparison, manganese content in this product is 10%. The present manganese ore treated by ERAMET has manganese content up to 50%. So no value comparing to classical ore. That the manganese residue dewatering. One very important thing is that you have to manage the chromium. In the ore there are some chromium. Chromium is dissolved, and you can have two different types of chromium, either chromium 3 or chromium 6. Chromium 3 rather simple to precipitate and to separate it from the solution, and it's not dangerous, as chromium 6 is very dangerous and you have to avoid it. And you can, if you put chromium 6 with the manganese oxide obtained by precipitation of manganese, if you put chromium 3 with manganese oxide, you create this chromium 6, and it's very, for the environmental part, is very deleterious, and you have to avoid it. And the conclusion is that you have to separate the manganese residue and to put it in a specific area. After that, to recover a pure nickel product, you will precipitate only 80% of the nickel. If you continue the reaction, you will precipitate also magnesium and other impurity you don't want to have. And the main consequence is that you have liquid with still some nickel containing in it, and you have to reprecipitate this nickel, remaining part of nickel, and to recycle it in the process. And the last part is a liquid effluent treatment to remove, you treat it with limestone to remove all the impurities and to have a very clean liquid effluent. Effluent, you see, that's not limestone, that's lime used for precipitation to have a very clear effluent. You separate by decantation all the solids, the suspended matter content in this effluent in order to have an effluent compliant with the environmental standard. All the questions regarding the environmental standard, we have to control the emission of liquid, of gas, and of solid. And all that are to be compliant with European standards and with local standards. On the liquid, you have to look at the heavy metals contained in the liquid, to the acidity of the liquid, to the suspended matter of the liquid, and to the temperature of the liquid. You have to have very, very low metal content, lower than 0.1 milligram per liter, acidity between pH 6 and pH 8, very low content of suspended matter, lower than 10 milligram per liter, and temperature difference with the sea lower than 10 degrees. When the sea is at 20 degrees, the temperature of the liquid will be less than 30 degrees. For the gas emission, you have to look at the CO2 emission for your process, and that there is no iron, no nitrate emission. For the CO2 emission, we have compared different processes. And this comparison is put in this diagram with here the production capacity of each plant. You see this bar corresponds to one specific plant, and the CO2 emission in ton of CO2 per ton of nickel. You see that depending on the processes, here you have nickel pig iron produced in blast furnace, very high CO2 emission at the level of 120 tons of CO2 per ton of nickel. Nickel pig iron produced in electric arc furnace, you decrease the CO2 at the level of 60 tons of nickel per ton of CO2 per ton of nickel. The saprolite smelting are at the level of 35 tons of CO2 per ton of nickel, and all the different hydrometallurgic processes at a very low level. You see HPL at 15 tons of CO2 per ton of nickel, and our atmospheric process is at a level of 4 to 5 tons of CO2 per ton of nickel. You see here that where our SLN in New Caledonia are, that's saprolite smelting at the level of 35 tons of CO2 per ton of nickel, and where will be our hydro process at very, very low level. That's very important to calculate all these emissions and to present processes with very low CO2 emission. Regarding the residue, you see this kind of residue. It's very important to know what to do with that, because there will be a huge quantity of solid produced, of inert residue produced. We will put it in big piles like that, and we will plant some grass or some trees on the residue, and to have a very green effect of the heap of the pile. And you see that our work in Indonesia, in Weda Bay, when you start a project, you have to, before the treatment of the ore, to imagine what you have to do with the residue and what kind of trees you can plant on the residue. And that was a test. You see Weda Bay in 2008, that's a part of the residue, and we have select some trees coming from the area, and in 4 years you see that the trees are at the level of between 2 to 3 meters high. That's very important to know what to do and what kind of species you can plant on the residue after the end of your plant. A conclusion of the process we have developed, you know, it uses very reliable technology, no pressure, temperature will be only at 100 degrees C. You can treat both limonite and saprolite, and you don't have to separate limonite and saprolite. It's a very independent energy process, very few fossil fuel consumption. The residue will be inert, you can store it very easy, and you produce neutral liquid effluent. And in our process we separate nickel from cobalt, and manganese is concentrated separately. To develop such process, you do that at lab scale on a small quantity, 1 kilogram of ore, 1 liter of solution. That's very easy, that's classical, but it represents only one part of the process. To have a global view and to simulate all the different loops of the processes, you have to do that on a pilot equipment with higher quantity. And at ERAMET we have done piloting at a level of 50 liters of solution per hour. When you do this piloting, it's campaign, 24 hours per day, 7 days per week, and up to 6 weeks long. You see 1,000 hours, it corresponds to 6 weeks. And between each campaigns you see which parameters you have to change to improve your processes and to be at the best level of processes. And from 2005 to 2013 and 2014, we have done 44 pilot campaigns to create a new process, and with a total of 104 weeks of piloting, more than 2 years of piloting to develop such process. For you it's rather simple when I present you, but there is a lot of difficulties and a lot of things you have to think and to manage during this pilot. The advantage of piloting is also to test the equipment and the materials you will use in the plant. You see that all the different equipment that you test, thickeners, filters, stirrers, crushers, effluent treatment, dryers, flocculant, solvent extraction, and so on, and the company involved in this equipment, and you have to share your process with these companies in order to have the best equipment on the world. And you see that guys from ERAMET, but that's guys from Autotech testing a very long thickener deconditioning column. You have to test also the material you will use for the different steps. We have tested different kind of steels. We have tested titanium, fiberglass, coating, rubber, brick lining, and so on, to be sure that at each stage you have the best equipment and that you will not dissolve the equipment with a very aggressive system. And during all this pilot testing, we were in contact with 23 equipment suppliers, and we have tested 45 different materials. That's the end of the third part of the presentation dedicated to the ERAMET process. Thank you very much. The next part will be the conclusion of the courseware.